So for your midterm, I think I will deliver on Monday. I just need, I think, about 10 to 11 students left that I still need to put your score in. So far, so good. I think the lowest score so far is around 60 something. So I think it's good. Average, I think average around 70 or 80. And starting from today until the end of the semester, we are going to focus on the vector calculus, which we start with the definition on the vector fields, and then move to line integrals, the surface integrals, also the curl and divergence. And if we have time at the end of the semester, maybe just an introduction to partial differentials. But I don't think you can have that. So I will focus on this vector calculus for a while. So if you see from some example here, of course that since we know what is vector, and in the this is a picture showing the wind patterns that can be elaborate as a vector. So basically this is an example for vector field applications. We can use for other application as well, like for the airflow, for the airplane, also for the blood flow, fluids, and then magnetic fields. It also can be modeled as a vector fields. And this is also example that we can have some simple equations. For example, we have the negative y in x-axis and x in y-axis, which if we connect all the some units, we can have this circulations. And also for sine x, we have like a something like we have curvy circulations as well, and we can have many functions in our vectors, and we can vary the functions, and we can have different results as in the vector fields. So far this is two-dimension vector fields, but of course we can have a space curve that we can also define the vector fields in 3 dimensions. This is just an example how we could draw the each one of the functions for each axis, and then we can have the directions for every part of unit. So usually, if you remember what we have in the slope field that we did in last semester in the Engineering Mathematics 1, in vector fields, we are going to split the measurement, maybe taking 1 units, and then based on that increments, we can decide which directions the vectors would be based on the equation. So we can maybe we observe from 0, 0, 0, and then maybe going for the x-axis first, and then going for the y-axis, and then going for any measurement in between, and we get the circulations like this. Okay. So basically, if we want to define a vector field, which means that we need to define the domain as usual, and also if we want to define the vector field in 3 dimensions, we can also define the domain that is going to be the domain will be also according to 2 dimensions, the domain will be 2-dimension vector, 3-dimension will be 3-dimension vector, and then so on and so forth. I think that's just for an introductions. That is for vector fields. And aside from the vector fields, if you remember the del functions, let's say if f is scalar function of 2 variables, then the gradient vector, or del f, it can be defined from our partials. Or simply, we can write this okay. Or if this is three variables, then we can have a 3 partials. And this is also a vector field, so we call this a gradient vector field as well. Okay, just a review of calculus on 2 dimension. And of course, if we have 3, we can have like that. So this is gradient. Okay. Now from this gradient vector field, there's another definitions that we call a conservative vector field. This is when or if it is gradient of scalar function. Let's take the conservative, let's name this as a capital F, and the scalar function is the small f. Okay. So if it is gradient of scalar function f, that is if there exists a function, the function f, such that this is equal. And when this happen, we call the small f is a potential function of f. So it's actually just naming the gradient vector that we have before. We can name it as a conservative vector field if we could have a potential function. Okay? If we could have from the vector field. And later, how to distinguish this conservative vector field, we are going to learn a little bit later. Okay? This is just an introduction. So we're going to learn a little bit later on how to determine whether the vector field is conservative or not. Okay, that will be on, I think, after we learn the line integrals. Okay, usually we start the vector fields with the curl and divergence, but I would like to start with the line integrals first, and then build up the definition until we get the curl and divergence. Okay, let's start with a definition first from the line integrals. Okay, so line integrals. Let's start with this picture before finalizations in the definition. Let's start with this curve C, and this is a parametric curve. Okay? So this is a parametric. And the curve will be based on parameter t, and I will define the t by taking all the function with the variable t, and t will be from a, according to this number, from a to b. Or we can write as a vector r and assumptions based on the picture. The curve C, we call this is a smooth curve. Okay? This is a smooth curve. If you remember the smooth curve, it is based on the curvature. And the curvature, if you look at the picture, is based on how to connect each dots. So for example, we connect this dots, right? And there is no sudden difference. For example, if you compare this with something like this, there is like a sudden difference. So it goes up and then suddenly goes down. It's not smooth compared with this. Here we have a steady changes, slow changes for every point, right? So we call that smooth. So that's our assumption, smooth curve. Which means, because it's smooth, then we call that the function r is, or maybe, right, smooth means the r prime is continuous. So r prime is not 0. Oh, it's not 0. Okay. And then if we look at the parameter from a to b, if we could divide the parameter becomes some small subinterval in between a and b, and then let taking the ti as a sample point. So divide the interval into some n subintervals. This is just like how we prove and define the integral. So we split and then we slice and then becomes a very, very small parts. And let the okay. And then the the curve C, will be defined into n we call subarcs. Okay. So it's arc, but we define become subarcs with length delta S1, delta S2, delta Sn. Okay, so delta S means the arc length. Okay, that is split between the from P0 to Pn. Okay, based on the interval the AB. Okay, now if f is any functions, of two variables that includes within the curve C, so evaluate f fxy, okay, at point, let's taking the sample point, which means any point between the subarcs that we already defined, and then multiply by the delta S, and then we can have a sum which we can see that this is basically similar to Riemann sum in the integrations, right? So that we can take the limit as the n getting larger and larger. Okay. So this will be the definitions. Then we move to here. That this is going to be, or let me browse to here, and let me add here. Okay, just to make it easy to see. So if the function is a smooth curve, okay, defined by the smooth curve C, given by equation 1 is the parametric equations. Then the line integral, so we now have a new definition. We call the line integral is the limit of the sum multiplication of the f and the delta s, okay? If the limit exists. And this limit we can rewrite as a line integral. Line integrals is integral, and then you put C on the bottom of the integral. That is for the curve C. Or it is supposed to be integration upon the curve, upon the curve. So you have a curve, and basically you integrate along the curve, okay? Along. So if we visualize what it is, if we take this example here, let me just put here. So basically this is the curve C. So the integrations mean we take this curve going up based on the functions. So that's the line integral. Okay, so that's the definition. But in practicality, because we want to compute this line integral in a simple way that we can elaborate more, then if we remember in calculus parametric, we know that the arc length, we can find the arc length, right? We can find the arc length. Now the arc length formula can be used for our line integral as well. So we can exchange and using the parametric equations. So let me write here. So remember that in calculus parametric, arc length is, if we have the a to b for the parameter, this is basically dx dt and dy dt squared, and this is dt, right? So this L we can take to our basically this ds, this is, let me just write here, this is actually the arc length, which we can substitute. So we can substitute and make it into, so the line integral becomes integrations from, so we substitute using t with parametric equations, and ds basically just put inside all the stuffs here. And basically this is valid for integrations with respect to t. And another perspective or of arguments that we can also provide, we can also see the arc length from the vector perspective. If you remember, we have the ds dt in vector functions, which this is the magnitude of the r prime t, which is also the same as the arc length in the parametric. So it doesn't matter which perspective we take, the conclusion is the same. So this is also the same with the arc length formulations. And to make sure that we get it correct, I mean the visuals is makes sense. We need to assume, not assume, but this is I think based on the definitions, the functions need to be a positive functions. So the line integral of the f, this will represent area of one side of the the fence. Okay, okay. Whose base is the line or the curve. Okay, so that's the definition of line integrals. So as long as we can define the curve as a measurement in length, and then we know the function of two variables, and we can connect the functions within the parametric equations, then we can evaluate any line integrals. Okay. So actually, if you see from the nature of the structure for the formula itself, because what we did here is basically assuming that everything will be a positive function. That means the only way we need to configure or make sure what is happening is we need to see only the curve. Right? We don't really care much about the functions, like this function here. As long as it is positive functions, it's okay. So we can just put everything inside. But we want to make sure that the arc length for the curve, it is smooth. It is smooth. Because there is sometimes, if, for example, the curve, for example, we can have a curve like this. Okay, it's smooth, but at some point, it's become like that, and then maybe like that. It means that the curve, okay, it's okay up until this point. So we know that from here to here, we know the line integral. Okay. From this point, we say, oh, this is problem. So another idea is we can split. We can make a complement. So we can have 1, 2, 3 curve. So 3 line integrals. Okay. So we can have C1, C2, C3. So we can also provide a split between the line integrals. So the total, for example, we can write this is C1 plus C2 plus C3. Okay, so this is another approach if we have some problems like this. Okay. Okay. So for instance, every time you have a problem in the line integrals, the only way you care for how to compute is make sure the curve. Okay, make sure the arc length of the curve. Okay. Okay. Next is I will give you maybe just a quick example. Also a review on the chapter 10 calculus. So if we have this questions, evaluate, we have so this is the function, okay, where the curve C is the upper half of the unit circle. So upper half, so we have a circle, right? We have a circle. So first is we know that this will be a circle. So since this is on the upper half, so I will erase the half one. So this will be where we say the y will be positive, right? Because on the upper part. And then for circle, parametric will be related to polar, right? So if we convert this, radius is 1, so x, or let me write, or now let me just use t, okay? Just to make it easier. Or here, since r is 1, so x is cosine theta, or t, y is sine. So the line integral this will be integrations from, now t is an angle now from, so if you remember polar, we start from theta is 0, or here is t equals 0 until this one, so this will be t pi over 2, this will be t equal pi, so this will be t from 0 to pi, right? And then change everything, so cosine squared t sine t, and then ds will be dx dt is sine, so sine squared plus, oh, I think this will be easy to follow, this will be 1, right? So 2 plus cosine squared t sine t dt. Okay, and then just a normal integrations. Or if you don't want to process, you can compute by calculators. I think it's straightforward, right? So this will be, if you want to compute, this is 2t plus, this will be cosine cube t over 3. Right? And then put 0 and pi. This will be 2 pi 1/3, 1/3 plus 2/3. Okay. And as I mentioned, I think in the last slides, that we can have this kind of curve, which means this is what we call as the piecewise smooth curve. So it means that the total curve is a union of finite number of smooth curves. Okay, you basically can split C1 plus C2 plus C3 plus C4 plus C5. So idea is we find all the points here. then we need to split out the C. Okay, just a quick example on how to look at the piecewise curve. Let's see this part here. Evaluate the line integrals to x ds. C is basically based on a parabola y equal x squared from 0, 0 to 1, 1, followed by vertical line from 1, 1 to 1, 2. So perhaps we start with the picture. So suppose this is the parabola. Okay, maybe that is. Let's say this is 1, 1. And then from here, we go a vertical line. Maybe that part is 1, 2. Okay. And then this is C1. This is C2. So for C1, we can see that if we focus on only on the C1, so I will try to compute this directly. So x is just x, okay, and y is x squared. So I will focus on how to integrating with respect to x, okay, directly. This is starting from x is 0 to x is 1. Okay. So the line integral for the C1 is basically 0, 1 for, I will using x as a integrations. So this will be 2x. And this will be 1 plus dy dx. dx. This is 1. dy dx is 2x. 2x squared will be 4x squared. Okay. Use substitutions, right? I think I can write here, taking substitutions. Okay. So 1 over 8. So we have 1 over 4, right? 1 over 4. So this is from 1 to 5. So this will be square root of u du. This will be 3 over 2, 2 over 3. This will be 1 over 6. Uh, 5. Three over 2, right? Minus 1. Is that? Yeah, I think we can just stop here. Okay, so basically this is for C1, but we still not solve for the final solutions yet. We need to consider the C2. C2 is the x is a constant. And y is just a regular line, y. And starting from 1 to 2 for y. So the line integrals for C2 is 2x ds. From 1 to 2, I will taking with respect to dy. So this will be 2, x is 1, right? And then this will be taking the arc length dx dy. Okay. If you want to write completely, you can just write this is basically dy over dy. Just similar with this one here, this is actually if you want to write completely, this is from here, okay, same. Now, dx dy is basically 0, right? Because x is a constant, so, but dy over dy is 1, so this will be 2 dy. Or we can just simply say this is 2, right? Because 2 minus 1 is 1. So the total is C1 to x ds plus C2 to x ds. This will be 5, 3 over 2 minus 1 over 6 plus 2. Okay. And yeah, that's it. And basically, the ds, the arc length, we can take it directly with x or y, depends on the conditions or the functions. Now if you see what we have here, basically we can take the dx into dx or into dy. And so we can have some I think simple approach. Okay, let's take a break for a while. Okay, so let's continue a little bit. So basically, we can have the line integrals. Let me write here, line integrals with respect to x or y. So if you're wondering, I'm taking most of the part, this line integrals sections from the calculus textbook actually. The engineering mathematics textbook have the same content, but I think I need to make sure that we have more familiarity with the contents about the line integral. So that's why I'm taking using calculus textbook, the factor calculus. Okay. So now we can conclude that the line integrals we can take with respect to x or y. So basically, we can replace, so we can replace the delta Si in the definitions by taking the delta Xi or the delta Yi. So that we can take the line integrals fxy dx. This becomes using limit definitions. Okay, or if we argue that the change is on the delta y, then we can also replace with delta y or dy in the line integrals. So the Riemann sum so we can basically write as this definitions. We can express, so we can express in parametric or in parameter t, so that the x, it will be xt, y is yt, so dx based on the chain rule, this will be okay, and that's why we have this. Okay. And sometimes, if we are setting up the line integral, I think one of the most difficult part is to think the parameterizations or the parametric representations for the curve. So sometimes we can also represent the curve with a vector functions. I think that will be more easier to approach. So this is easier to approach. Let me write here. So we can express using the vector functions. So this is the vector representing or representation of line segment. start from R0 and ends with R1. Okay, now if we have problems like this, okay, in example 4 here, we have two paths. Okay, we have two paths. So we have two conditions. So we need to evaluate the line integrals y squared dx plus x dy for two different paths. Okay, for two different paths. We can have C1 using this line equation, or we go here and taking this parabola, and we have the points -5, -3 until 0, 2. Okay. So we can use this or use this. So let's try out and make some conclusions at the end. Now, for the line segments, since it is from this point to 0, 2, we can write as a parametric representations. So parametric. So if we start taking from 0 to 1, basically we are going to plug in the initial points and the end points x and y, so that we can have x equal, this will be 5t, since it is -5, so -5, -t, 5, right? Minus 5. And y will be 0 and 2. This will be 5t minus 3. This is, or let me write. This is using. Let me write here. T is 1 minus t. Okay, so that's line segments, and we evaluate then C1 y squared dx plus x dy. Okay, I think we can use our parametric. And taking the, or let me maybe let me write first the the derivative is dx is 5 dt, dy is also 5 dt, right? Okay, we can substitute. And then using the parametric 0 to 1. So 0, 1. This will be y squared is 5t minus 3 squared 5 dt plus 5t minus 5 dt. Okay. We can factorize 5. This will be 25t squared 25t 75t okay. So this will be 25t squared negative 25t plus 4 dt. I think easy to compute. This will be 25 over 3 t cubed so this will be 50 over 6 minus 75 over 6, so negative 25 over 6, negative 24 over 6, so this is negative 1 over 6, so negative 5 over 6. So this is for C1, right? Okay. For B, using this C2, since we have parabola x equal 4 minus y squared, so then we can just use y as just y, just as it is, and then we can take y from negative 3, right, to 2. So we are going to focus using only y. So then the line integral so we are going to change everything using the dx is negative 2y dy. So we can exchange this part. So this will be equal y squared. Let's just take that y squared. This is negative 3, 2. Dx becomes negative 2y dy plus x is 4 minus y squared and then dy. Okay. So this will be negative 2y cubed negative y squared plus 4 dy. Okay, I think easier to compute. So this will be negative, okay, and then this will be y cubed over 3 plus 4y you can check using calculator, but this is supposed to be 45 over 6. You see that we have this two different value at the end. So it means that the curve will be important to our calculations. Okay. So let me write here the value of line integrals depends not only the endpoints, but also on the path. Okay. With the same approach, we can also write the line integrals in space. Let me write here, I forgot to write this. So line integrals. Okay, so suppose that we have all parametric in terms of 3 axes, and we define from A to B for the parameter, or we can describe this in the vector R. And we say that if fxyz continues on some region or area containing curve C, then we define the line integrals of that fxyz ds is equal limit and similarly using the same formulations in the two variables, then we can write the line integrals. And taking the arc length. So now the curve is not in 2 dimensions, but it's in space. And we can rewrite the line integrals in more simple notations. We can use the vector R. So the functions base, we can write with the RT, and the square root will be our magnitude value of R prime. And for case that is, if we let the functions equal to a constant, then we can just integrate only ds, which means that this is only taking integrations of the r prime t dt, which is equal to our arc length. We can also define line integrals with respect to x, y, or z. For example, and in conclusions, because we can define with respect to x, y, and z, then let me write this code here. Then we can rewrite rewrite and then can express x, y, z, dx, dy, dz. We can express in terms of parameter t. This is, let me just remove that. And let me give you example on this part. Evaluate so evaluate this line integrals where the curve is circular helix given by the equations. I think after 2 examples, I think I will finish the class. And z equal t. So if you remember this, in xy plane it's a circle, but since it's increasing every increments of t with z axis, so the circle is going up and up, like a DNA. So it's like so it's going up like that, circular helix. Okay, maybe not really proportionate, but this is supposed to be how it looks like, the circular helix. So the line integrals y sine z is basically oh, the question should be also comprised with the parameter, which start from 0 to 2 pi. Okay. So we are going to change everything in terms of parameter t. So this will be integrate with respect to t. So y is sine. So we can substitute all and this also can be written as all the first derivative and then squared and then dt. Okay. So this is sine squared. This is cosine squared. And this is plus 1, right? So this is 1, so this is 2. So sine squared 2, square root of 2 dt. You can use double angle formula for this. And the sine part will be 0, right? So this will be square root of 2 pi. Okay. I think not really that complicated. Another example, last example. Evaluate the line integrals Okay, so this example have several line segments. Only two. C1 is from 2, 0, 0 to 3, 4, 5. And followed by line segment C2 from 3, 4, 5 to 3, 4, 0. I think we can draw the picture. Suppose this is Z, this is X, this is Y. 2, 0, 0, let's start from here. This is 2, 0, 0. And then 3, 4, 5. Maybe 3 is here. 4 is there. And maybe 5 is here. So 3, 4, maybe 5 is here. So let's say this is C1. This is 3, 4, 5. And 3, 4, 0, it's going to be this. Right? Okay. We can use the vector functions and using R0 and R1 using the points that we have. Okay. Using the vector positions. So 1 minus t using the, and we can take the vectors 2, 0, 0 plus t 3, 4, 5. This is for C1. So this is for C1. So solve this, okay. This will be 2 plus t. Two minus t plus 3, so 2 plus t, 4t, and 5t, okay? So that's our vector r. And then the line integrals or we can write in parametric based on the vector just to make sure. The vectors itself or the parameter itself is from 0 to 1. So this is 0, 1. Y is 4t. Dx is just 1, right? Dx is, 1. So this is dt plus z is 5t. dy is 4. So 4 dt. X is 2 plus t. Let me make it more clear. Two plus t, dz is 5. Okay, so we solve this. I think no problem, right? So just plus 10 plus 5, 20, 25, 29, right? And just integrate. This will be 10t plus 29t squared over 2. Plug in. So 10 plus 29 over 2 is 14 plus 10 is 24 or 0.5. Right. And the same thing with C2, we can do similarly. You can take the RT 1 minus t. Now start from 3, 4, 5. Ends with 3, 4, 0. This will be 3, 4, and then 5 minus 5t. So x is 3, y is 4, and z is 5 minus 5t. So using the C2 to integrate y is 4, dx is just dx, I think 0. Oh, I think because y and x is constant, so every dx dy becomes 0. So we only have x dz, which is x is 3 and dz is negative 5 dt. So we only have this, which is negative 15, right? And the total, then we just add these two numbers. So this becomes total is 9.5. Okay. So I think I will end up until here. Okay.